keep in mind, I mentioned that for general regions, just changing the order of integration and the variables of integration will not give me an equivalent integral. So let's talk about order of integration for general regions. There are times when I might get a region that is actually bounded on the top and bottom by two continuous curves, as well as on the right and left by two continuous curves. In these cases, we're going to have two choices for our order of integration, and we'll need to choose our order of integration in a way that will minimize our work and the risk of making mistakes. We may even find that we've got to change the order of integration when our first option ends up not being expressible in terms of elementary functions. It is extremely important to make sure that we accurately identify the limits of integration when we evaluate any regions of this type. Here's an example. I want to reverse the order of integration for the integral that's given by the integral from 0 to 3 of the integral from 0 to 6 minus 2x of f of xy dy dx. So I'm going to plot the boundary of my cross-sectional region. I'm bounded by the x-axis on the bottom, the y-axis on the left, and the line y is equal to 6 minus 2x on the right. My outer integral takes me from 0 to 3 in x, and my inner integral takes me from 0 to 6 minus 2x in y. But I want to reverse the order of integration. So I'm going to plot my region here, but I'm going to rewrite the equation for the bounding curve on the right by solving y is equal to 6 minus 2x for x. I'm going to get x is equal to 6 minus y over 2. This means that I'm going to take the integral from 0 to the curve 6 minus y over 2 in x, and then the limits of integration in y will go from 0 to 6. And this gives me the integral from 0 to 6 of the integral from 0 to 6 minus y divided by 2 of f of xy dx dy. In order to change the order of integration, I have to solve the boundary condition that's given in terms of a function of x and make it a function of y. Here's another example. I'm given an integral that can only be evaluated here if I change the order of integration. I'm going to sketch the region of integration and determine the limits of integration that will be needed to reverse the order of integration, and then I'll evaluate the integral. The integral I'm given is the integral from 0 to 2 of the integral from 0 to 4 minus x squared of x times e to the 2y divided by the quantity 4 minus y dy dx. I'm going to sketch my region of integration. I have a downward opening parabola that's described by y is equal to 4 minus x squared. My region is bounded on the left by the y-axis and at the bottom by the x-axis. My parabolic curve intersects the y-axis at 0, 4 and intersects the x-axis at 2, 0. The given order of integration asks me to integrate from 0 to 4 minus x squared first, and then to integrate from 0 to 2 in x second. I need to swap those orders of integration. I'm going to redraw my region and rewrite my equation for my parabola as a function of y. My function becomes x is equal to the square root of 4 minus y. Notice I choose the positive square root here because this is the positive portion of my graph. I'm going to now integrate from 0 to the square root of 4 minus y in x, and then integrate from 0 to 4 in y. This gives me the double integral from 0 to 4 of the integral from 0 to the square root of 4 minus y of x e to the 2y over the quantity 4 minus y dx dy. Now I want to evaluate the inner and outer integrals. The innermost integral is the integral from 0 to the square root of 4 minus y of x e to the 2y over the quantity 4 minus y dx. This gives me x squared e to the 2y over 2 times the quantity 4 minus y, evaluated from 0 to the square root of 4 minus y. I get the quantity 4 minus y e to the 2y over 2 times the quantity 4 minus y. This simplifies to e to the 2y divided by 2. Now I plug that first integral result back into my outer integral. I get the integral from 0 to 4 of e to the 2y over 2 dy. This becomes e to the 2y over 4 evaluated from 0 to 4. My final result is e to the 8th over 4 minus 1/4, or e to the 8th minus 1 over 4. Now I want to examine more general volume problems where the volume is actually bounded between two surfaces. The integrand in these cases describe the difference between the top and bottom, or the right and left surfaces of a 3D volume. This difference of the two functions gives me the height of my 3D solid. So my volume is given by the double integral over the region R of g of xy minus f of xy dA, where g of xy is the top or right surface and f of xy is the bottom or left surface. Let's work an example. I want to find the volume bounded by the paraboloids z is equal to x squared plus y squared and z is equal to 50 minus x squared minus y squared. It can be challenging to construct a 3D plot of these surfaces, so we need to be able to examine our surface functions to determine what our top and bottom functions are and whether we want to integrate with respect to x or y first. Our first surface is an upward opening paraboloid, while the second is a downward opening paraboloid that has been shifted upward by 50 units. My top function will be given by z is equal to 50 minus x squared minus y squared. The two surfaces meet at a plane where x squared plus y squared is equal to 50 minus x squared minus y squared. This meeting point gives me a circle described by x squared plus y squared is equal to 25. In other words, my two surfaces meet at a circle centered at the origin of x and y with a radius of 5. Our limits of integration for our outer integral will be from -5 to 5. So using this circle function, I solve for x. X is equal to plus or minus the square root of 25 minus y squared. This tells me that my double integral will be an integral from -5 to 5 of an integral from negative the square root of 25 minus y squared to the square root of 25 minus y squared of the function 50 minus 2x squared minus 2y squared dx dy. I compute the integral from the inside, and I get the integral from -5 to 5 of the quantity 50x minus 2/3 x cubed minus 2y squared x, evaluated from negative square root of 25 minus y squared to square root of 25 minus y squared dy. This gives me the integral from -5 to 5 of 200 over 3 times the square root of 25 minus y squared minus 8/3 y squared times the square root of 25 minus y squared dy. This gives me the quantity 200 over 3 times the quantity y over 2 times the square root of 25 minus y squared plus 25 over 2 times the inverse sine of y over 5 minus 8/3 times the quantity y over 8 times the quantity 2y squared minus 25 times the square root of 25 minus y squared plus 25 squared over 8 times the inverse sine of y over 5, all evaluated from -5 to 5. Being extremely careful with the algebra that is involved with substituting my limits of integration in here and being very careful to watch for my signs, I end up with a result of 625 times pi. Note, there are steps I'm leaving out, but they involve algebra only. Now it's your turn to try it. Pause the video and find the volume of the solid region above the parabolic region defined by the region R is given by the sets of all points x, y, such that 0 is less than or equal to x, which is less than or equal to 1, 0 is less than or equal to y, which is less than or equal to 1 minus x squared, and between the planes z equal 1 and z equal 2 minus y. When you're ready, restart the video to check your understanding. I want to find this volume of this solid region above another parabolic region that's defined between 0 and 1 in x and between 0 and 1 minus x squared in y that lies between the planes z equal 1 and z equal 2 minus y. The two equations for z give me my upper and lower surfaces. The upper surface is z is equal to 2 minus y. The lower surface is z is equal to 1. If I observe the allowed values for x and y in my region, I am going to choose to integrate first with respect to y and then with respect to x, so that I get the integral from 0 to 1 of the integral from 0 to 1 minus x squared of 2 minus y minus 1 dy dx. This gives me the integral from 0 to 1 of the integral from 0 to 1 minus x squared of the quantity 1 minus y dy dx. I compute the inner integral and I get the integral from 0 to 1 of the quantity y minus y squared over 2 evaluated from 0 to 1 minus x squared dx. This gives me the integral from 0 to 1 of the quantity 1 minus x squared minus 1/2 times the quantity 1 minus 2x squared plus 4x to the 4th dx. This is x over 2 minus x to the 5th over 10 evaluated from 0 to 1. I get 1/2 minus 1/10, and this reduces to 2/5. This is how I can find volumes of solid regions that involve having curves that may bound my region of integration at the top and the bottom and or the left and the right. Be sure and let me know if you have any questions.